gracias. Today we're going to talk to you a little bit about car hacking and car security, and have an overview of some of the attack surfaces that we've worked with. So this is Don't Be a Dummy, a crash course in security. There'll be plenty of terrible car jokes, so brace yourselves. So, the dream. We've all grown up watching movies and TV that have cars with intelligence and that have special features that we one day hope would be a reality for us. So things like the Batmobile, iRobot, everyone's favorite, KIT. In reality, this is what we have right now. And this is actually an amazing accomplishment, nonetheless. But one day, maybe we'll have something like James Bond. This is an older BMW, but BMW has promised to have a fully autonomous flagship for 2021. So, concept art there. Hopefully it helps you dodge bullets as well. So, a little bit about who we are. You just got the introduction, but I'm Drew Suarez, a principal security consultant and research director with the NCC group. My background is primarily mobile on the Android side, but recently getting more into the IVI and low-level firmware and system updates for automotive space.
Hey, and I'm Daniel. I'm a regional director with NCC Group. We were both out of the Chicago office. I've been doing Automotive work with Drew. We spoke here last year, actually, so I'm glad to be back. And we also do automotive work. Now I'm more about threat modeling of car systems and talking about CAN bus and things like that. NCC Group, we are in Chicago. We have a bunch of offices in North America, but we also have worldwide offices since we're based out of the UK.
Cool. So a brief outline of what we're going to be talking about today. We'll have a brief introduction to the automotive security space, and then we'll talk about the topology and threat model of vehicles, and then we'll take a much deeper dive into the attack surface. And then finally, our last section is called Jumpstart Your Research, and we're sort of hoping to get people involved in this space. So we'll have a lot of information on how you can get started there. So we'll start with the introduction to the automotive space. So the first question is why now? Why is this such a hot topic? Why do you keep seeing car hacks and things in the news? So I think traditionally, car security has been focused primarily on passenger safety and physical security, so making it harder for someone to steal a car. But modern cars are much more connected now. Your car is on the scary internet at this point, in some cases. So the attack surface has changed, and it's changed very fast. And the push towards self-driving cars, as we showed earlier, there's many more ECUs in the car now, and things are much more connected than they used to be. So there are components that were relatively safe before because they were unreachable, and now they have potential attack vectors. And the potential for harm of people has become very real as well. I'm sure everyone's seen previous stories about controlling a Jeep on a highway and things like that. So these threats have become much more realistic. And as I said, new technologies bring about new attack surfaces that hadn't previously been thought of. So that's why we're seeing a lot more of these things now in the news. So I want to talk some about the unique challenges that the automotive space encounters, which lead to security issues. The first is supply chains. There's very complex arrangements that leave OEMs, like car makers, very little control over some of the parts that they use. They just get what they get, and their influence on their tier one suppliers is pretty limited in what they can ask for and integrate. And there's very long development times with automotive space. Something like today, a car that will come out 5 years from now has already been signed off on and written up, and the plan is already in place for that. So that leaves a lot of outdated software and technology that can happen in that span of 5 years. That's very hard to update, in time for that to come out. And there's no official security standards. There's lots of security standards out there, but nothing that's like actually mandated in some cases for some of the things that we'll talk about here. And vulnerabilities often go unpatched for the lifetime of your vehicle. I think compared to mobile, a lot of people will buy a new phone every 2 years, but when you purchase a car, that's something you're going to have for a significantly longer amount of time. And so these problems that may have shipped day one will be with you for the lifetime of that vehicle. And because of the long development times, code and configurations are often reused over and over and over. So these bugs will be essentially copy and pasted for years to come because it's much easier to use something that's already written and put it into something new than it is to change that. And then there's somewhat of an embedded system developer mindset, and that's something I mentioned earlier, where the people that write code for these ECUs never dreamed that it would be reachable from the internet one day. So there's a lot of legacy code out there that was not written very well that can cause problems. Usability and passenger safety. So these requirements typically trump security concerns, and I think we're seeing that finally start to change. And the industry is now realizing that security bugs actually can translate directly to a physical safety and a passenger safety issue. And there's really no consistent threat model here, and I think that's probably the most damning thing, is that every OEM has a completely different design internally, and even OEMs that make a lot of cars, those cars have different designs and topologies, so it's really hard to have a consistent threat model because it's wildly variable. And it's a hard problem to address as a result of the number of variations that exist out there. So there's a number of standards I mentioned. They sort of made this graphic to show a few of the more common ones. The problem for this is it's a huge barrier to entry for people trying to learn about this because these standards are proprietary and not freely available in most cases. So in order to even get this kind of information, it's an expensive process to learn about what these standards are and what they cover. So I think it's prudent to talk about some prior research in this space, and these are things that you guys have probably all seen before. But attacks on things like keyless entry. Sammy Kamkar has some great research out there on keyless entry attacks and problems with these. And here's pictured as his roll jam device, which is used to attack keyless entry systems. There's also the Megamos crypto issues that Volkswagen had, and this is something where Volkswagen actually sued researchers and prevented them from publishing this information for a number of years. And so, I think this is changing now, but a lot of these car OEMs have been stuck in this 90s mindset of we're going to sue people instead of welcome, valuable research and accepting help from people. And so, moving on, the remote unlock, things like OnStar. Again, Sammy Kamkar has some interesting research in his OnStar. And this is basically a direct result of a very poorly configured mobile application that ran on smartphones. I'm sure everyone's familiar with the Charlie Miller, Chris Valasek, GPAC. There's some great papers out there if you want to read all the nitty-gritty details on that. And then prior to a lot of people in InfoSec getting involved, period, in this space, there's been some great academic research out there and some papers that we'll link at the end if you want to read from Carl Kosher and Stephen Checkaway, et cetera.
So thanks, Drew, for the introduction into all these problems or the challenges which we're facing there in the space. So now we're diving a little bit more into what is a car made out of, and what can you attack, and what's actually the threats which you have and what you should be concerned about as a security person. So here's a picture of a modern car, and you see there's a lot of different systems which are integrated into this. It starts from an infotainment system. You have remote diagnostics or telematics units. You have adaptive cruise control, which can automatically brake your car if the traffic brakes in front of you and accelerate again. We can have wiring, which is exposed on the outside, so somebody may be able to get close to the car and tap into these wires directly. We have tire and pressure monitoring systems, remote keyless entry, which Drew already mentioned, and then a variety of sensors that could be for parking, for LiDAR, and other kind of things. as well as rear seat infotainment. If you think about riding in a cab and you have an infotainment system in the back seat or something like this, that's potentially something how you could attack a car as well. And so this just meant as an overview. We will talk about a few of those in a bit more detail and how they play a role for attacking vehicles. So the first thing is that all cars are made out of a lot of electronic control units called ECUs, and they're distributed throughout the vehicle. So you have an ECU which controls your airbag, one which controls the lights, one which controls steering and braking, and every one of those has one which is basically dedicated for a specific task. And we're adding more and more to these. In like a modern car, we may have like 60 to 70 ECUs which are part of the vehicle. The most powerful one of those is probably the in-vehicle infotainment system, or IVI as it's usually called. That's the thing you have in your dashboard that has a screen or some sort of way to interact with it for radio, and for modern cars maybe for navigation and things like that. And this one, they usually have a pretty big attack surface. On top of those, we have sensors which are connecting onto the outside world. So we may have something like LiDAR or radar, which is used for self-driving cars now, for lane departure warnings and things like that. We have parking sensors, which we have for a long time, which are just making beeping noises when you're like trying to park. And there's a rear-view camera in a lot of new cars now, which also takes information from the outside world. So all these things are connected. There's vehicle buses which are connecting all these things. And each of the different ECUs is usually connected with one of those. And there's different technologies, and they're pretty specific to the automotive space and maybe some other areas in the transport business. The most common one is the control area network, which you may have heard about, which is the CAN bus. This is most common because almost all cars which have been built since the 90s have some sort of CAN bus interface. It's just I'll talk about in more detail about it, but it's basically a two-wire bus connecting components, and they can send messages back and forth. And besides CAN, there's other ones, which is DLIN and MOST. MOST is more for media and video streaming. It's a fiber optic connection. FlexRay, and now more modern cars actually are moving to Ethernet, which we know as a more modern standard from other industries. So at least we understand this a bit better than the older standards. So the CAN bus is pretty simple. We have a graphics over here. I guess this laser pointer doesn't work. So the CAN bus in the middle is basically like a system which is a broadcast system, and every component which is connected to it can talk to this bus. And there's no authentication. So if you have a physical connection to this bus, you can send a message on it to anybody. And nobody knows who it's coming from because there's no from address. The only thing is an arbitration ID, which is just 11 bits, and that one specifies who the recipient of this particular message is supposed to be. There's some collision avoidance. If multiple people are trying to send at the same time, the one which has the lower ID will have a priority. And the goal here is that if you have a safety critical system, that one has a lower priority, so that if you increase your temperature in your AC, that's maybe not as important as deploying an airbag if you're in a crash. So there's a priority between those things. And this happens at like a whopping speed of 500 kilobits per second. Compared to like anything else we know, this is like really slow. But this is the high-speed variant of CAN bus. The data which is being sent is fairly simple. It's down there. It's like a little block diagram. It has this 11-bit ID, which just specifies who the message is for, a data length, and then the actual payload. And also the payload is pretty slim. It's only 8 bytes of data. So there's not really much data which we fit in one of those messages. So in order to send larger messages, there's other protocols which are built on top of CAN. The most popular one is ISO-TP, which has an ISO standard and is internationally standardized. And the idea is that you can chain multiple ones of those CAN messages together. So you will have a header which basically has an ID for each different message, and you can then send less per frame, but you can actually in total send 4 kilobytes of data. And one popular way how this is being used in cars is the unified diagnostic system. Again, this is something which has been in vehicles since the 90s, and it's meant for repair shops to be able to diagnose engine problems really quickly. You have probably an OBD2 port in your car which you can plug into, and you can read error codes, and those error codes are coming usually via UDS. The interesting thing is that while the UDS is standardized, the actual codes for errors are not. So if you have a Renault or you have a Volkswagen, it's very different in what error codes you have. So you have to have different tools or different tables to figure out what actually is wrong with the vehicle. One little quirk here is kind of interesting. I mentioned before that there is no sender in any of the CAN messages. So if you're asking for a diagnostic code from an ECU, how do you know what the response to that is? Because you don't know who's sending like a response message. And there's like just basically a rule that you take the ID of the ECU which you're talking to and you're adding 8 to it. And if you see a message with that address, you know it's a response to your request previously. Talking about security, there is basically, as I said, for CAN, there is no real security on it at all. And for UDS, there is like very basic ones. There is called a kind of a challenge response algorithm where the car has a secret and the diagnostic software from the manufacturer has a secret. And if you want to perform a sensitive operation, then you will get the challenge from the car, and you use that secret you have to calculate a response, give that to the car, and the car verifies it. But very often, the challenge and response are pretty static, and there is actually not much randomness going on, so you may be able to just record it once, and then you can replay it at will. So there is security, but not really. So this is the graphic I've showed you before, where we have things connected, and I was oversimplifying this a little bit. In like a modern car, typically we don't have everything connected to one CAN bus, but we have something like this, where we have multiple CAN buses. And here you see the powertrain and the airbag are connected to one, which is a bit more sensitive than the second CAN bus, which has HVAC, which is the air conditioning system, and maybe infotainment and things like that. And then we connect those using a CAN gateway. And you can think of this as being like a router or like a firewall a little send a message from one side to the other, it has to go through there, and you can enforce rules that, for example, the HVAC system never needs to talk to the powertrain, and so that would be blocked in one of those, so that you have some sort of segregation of the different components. And so if you look at a modern car, this is taken out of Charlie Miller and Chris Valisek's paper. Each of these boxes represents a different CAN bus. So if you look at cars which are being produced these days, there is multiple ones of these CAN buses, and they're connected in some way through these gateways. So it's not so simple anymore that if you get access to one of these CAN buses, you don't necessarily get access to another component. So if you attack some ECU which is connected to one CAN bus, it doesn't necessarily mean that you can compromise a different part of the car in the end.
Thanks. So let's take a more detailed look at the attack surface here. So we first want to talk about local versus remote, and that should be fairly self-evident, but when we say local, we mean things like an attacker physically has to have access to your vehicle. So things like an exposed USB port, ODB2 port access, in some cases direct CAN bus access, or physical disassembly of a component. Whereas a remote attack is something that the attacker doesn't have to physically be in the vehicle to achieve. So things like Bluetooth and Wi-Fi and NFC, like things you're familiar with, and cellular, which is the much more interesting target there, because you can hit that from the internet in a lot of cases, and it could be hundreds of miles away from the vehicle. So how exploitable are some of these problems? So we want to say mass compromise, which is something either local or remote that has a massively widespread impact. So something that impacts thousands of vehicles across multiple models, versus something more targeted, which is a little bit more nefarious to figure out, because this is usually a specific target in mind, one person's vehicle in particular. I mentioned briefly earlier telematics. So these allow your car to send and receive telecommunication data, and they require access to data from multiple different ECUs in your vehicle. So there's a few standards out there, IEEE 802.11p, GSM and GPRS modems, and the newer next generation telematics protocol. And this puts your car on the scary internet out there. There's also things I mentioned earlier, like remote keyless entry. Many of these use very poorly constructed cryptographic implementations and have a poorly made smart app component to go along with that. And these, in many cases, also provide remote keyless ignition as well as remote keyless entry. There's things like rear view cameras, which are externally accessible on vehicles. And something that a lot of people may not consider is that this video stream is processed almost always by native code. So you have C and C++ parsing happening in your vehicle. So things like we've all heard of stage fright for Android, but these are very real possibilities for things that your IVI is running and things that they're parsing. And something that seems very plain and innocuous, like a tire pressure monitor, that doesn't seem very scary. But these are connected to other ECUs in your car. So this could be a pivot point, like an initial foothold into a vehicle, because these all communicate with unencrypted RF communication. So if you can hack a tire pressure monitor, you might be able to pivot to a more crucial ECU somewhere in the vehicle.
Yeah, and then this brings us to the infotainment system, which is like the biggest part of all of this. It's the ECU which has the most attack surface in most vehicles, and it runs a variety of different operating systems. There's can be QNX and Linux and a few others. And it also comes with different capabilities and configurations. We see if you have an entry-level car, you may only have a stereo, which doesn't do much. And if you have like the luxury brand's car, then you may have it being internet connected. You have GPS and all kind of other features. So how would we, or what's the concern with the infotainment system here? Because you would maybe think, well, if I'm getting into this infotainment system, what do I gain from that? It doesn't really talk to my car much. So this is kind of how this is usually set up in most infotainment systems. The right side of this is showing you the side of it you're interacting with. This is like what a user usually sees. And then the left side is the car systems. So when we look at the right side, we have things like USB, and over USB you may have Apple CarPlay or Android Auto. You may have a video decoder which shows you your rear view camera when you're parking. You have a screen connected to it, a number of buttons. You have Wi-Fi and Bluetooth and NFC and maybe TV, maybe satellite radio, maybe HD radio, maybe CDs, GPS. So all these things are packed into one unit which you have in your car, and all of these are connecting somewhere to the outside world which you can potentially attack. So and then all this is running on the SoC on the right side, on the system on a chip, which is the more powerful processor in there and which provides all of these functions. But at the same time, if you think about what you can do with these units, usually you can also adjust your air conditioning temperature, or you can see the tire pressure, or you can see when service is due, or if something is broken. So in order to get all that information, it also needs to connect to other car systems. And so usually there is a separate chip, which is called the I/O chip, the IOC here. And that one is actually connected to the CAN bus and maybe to different radios, microphones in your car, steering wheel controls and things like that, fans for AC, all these things are connected to that side. And then the two of them are connected using SPI, for example, which is just a low-level protocol to talk between chips. So they are separated, but then if you get access to the SoC, you can still talk to the IOC. And that really depends on like how the specific head unit is made out of to determine what you can do with that. If you can reprogram the I/O chip to send different messages, like Charlie Miller and Chris did, or if there is any other way to influence what the car does once you compromise the right side. So if you look at these, the attacks again from like the local to remote attack surface, which Drew kind of mentioned. If you get physical access to the car, you always have to think about if you have physical access to the car and you want to do something to it, you can do usually far worse things because you can cut brake lines or you can do other kind of physical harm to the car. But for like the electronic side, you can obviously plug into USB. You can look at hardware debugging such as JTAG, or you're looking at a serial console which may be on there. There's applications which are in the head unit itself, which you may be able to hack. And there's oftentimes other kind of serial interfaces which are used for internal processes which you may be able to get connections to. And then obviously, the CAN bus in a way is like the target you want to get to because it's connected to so many vehicle systems. And one of the ways is the UDS, which is exposed via this OBD2 port. So you can plug into this, and then you may be able to do things such as changing the VIN number. So if somebody steals your car, they may be able to change the VIN number, which is the vehicle identification number, to basically, if somebody reports it stolen, the car will think it's a different car at that point. So there's like ways to connect to these kind of systems. And then if you're looking at the remote vectors, I kind of hinted at those already. Bluetooth, Wi-Fi have a pretty big range, and any vulnerability which we know from those areas, you can potentially exploit in like a car system. NFC is usually used just to pair with Bluetooth, so it's not often that exciting. But you may be able to pair Bluetooth by just remotely reading that NFC reader. And then satellite radio, GPS, it's something which hasn't been much research on, but that's digital data. If you can forge a signal from digital audio broadcasting or GPS, you may be able to exploit a ECU based on that. And then lastly, telematics is kind of the scariest of them because it's actually connecting to the internet via GSM, and that's the way how you can get to it from anywhere on the internet.
Thanks, Daniel. So we mentioned earlier that these IVI systems run a variety of different operating systems. So these are the most common ones that we've personally seen. A lot of the aftermarket ones run Android, and they run very out of date and thus unpatched versions of Android. So this is usually very trivial to gain root access immediately if you have one of these systems. And as Daniel mentioned, a lot of these have like a UART interface or a serial interface you can connect with UART, and a lot of them just drop you into a root shell to begin with. But if not, there are lots of publicly available ways to root the Android that's running on the IVI. The interesting beast here in the middle, QNX or QNX, is a very strange, to me, real-time operating system in a Unix variant. But it's very frustrating to work with because there's almost no user land binaries to speak of in these systems. And so you have to kind of roll everything yourself. And you also do not have the privilege of access to like tons of libraries and headers that you might on another Unix system. So you're sort of locked into getting a trial of their compiling environment. So you can sign up for a trial and cross-compile your own code. And it's fairly non-trivial to get this working. I think I burned a couple days trying to just simply get files on and off one of these systems. And I had to eventually find like a 1984 version of Netcat and compile that from a single C file just to have the capability to push files on and off this thing. So it's quite frustrating to work with, and we definitely suggest building a tool chain to work with this because you're going to have very little to work with in the supply to user land most of the time. QNX is fairly well documented, but sparse on the details that you actually want when you're trying to attack a surface like this. So there's lots of information on it, but nothing that I found all that personally useful in a lot of cases. And then lastly, Linux is also out there deployed. This is obviously the easiest to instrument and test because there's tons of publicly available tools out there to help you with your explorations. And these are kept more relatively up to date compared to, we've seen these things, modern IBIs shipping with Android 4.1, like multiple years old versions of software. So the interesting components here in the IVI, software updates. So typically, these are done via plugging a USB stick into the unit, or in some cases, there's over-the-air updates. But the same typical issues you might expect from other areas of security are prevalent here, such as lack of or very weak signing of these updates. And in many cases, lack of or no integrity checking. So you can just simply put your own files in these updates and have the system just slurp it in and install it for you in a lot of cases. These are obviously getting better, but there's many systems out there with these issues. And this execute is root. So if you can get something of your own to run at install time, it will actually execute as root. And you can thus gain persistence on these. A lot of systems we look at have sort of like a dual file system where if it detects that one of them has been tampered, it will fail over to the other one. But you can actually update both in many cases if you're clever, so that doesn't happen and you gain persistence that way. And this also allows you to update critical firmware. So you can update like IOC firmware using one of these updates, which will get you a very nice foothold in the system. There's vendor smart app controls. A lot of the software we've looked at has been very poorly constructed. And these allow you to do things like unlock your doors remotely start your car if it's cold in the winter and you don't want to go outside. It also tracks your fine-grained location and things like that. And as I mentioned, a lot of these are very poorly constructed. So there's hard-coded secrets, there's hard-coded crypto, interceptable communications like poor TLS implementations that allow you to man in the middle of these communications. And sort of an interesting attack vector there is that a lot of the backend servers expose API that is not actually in the UI of the smart app. So if you start messing around on the backend, there's much more functionality than you're actually presented with on the user interface side. So there's interesting and fun things you can do with those.
Yeah, and then in addition to, there we go. In addition to this generic, it's this integration which Drew mentioned for controlling things such as unlocking the car, we see more and more smartphone integrations. So the issue with smartphones is if you can compromise a mobile phone, if you have an Android phone, for example, or which get rooted remotely, or you have a jailbroken iPhone, which somebody could compromise, then you connect this to your car, and then you suddenly have a channel from a phone to your car, and then you may be able to compromise the car via a phone. So what we see here is that there's two different types. There's the OEM-specific integrations, which are an app which you have on your phone, which is specific to a certain car manufacturer. So you have Toyota has Smart Device Link, Ford has Sync, Harman has AHA, and there's a bunch of other specific ones which are for a particular vendor. And those usually use some sort of proprietary protocol which talks over some serial connection over Bluetooth. That's usually what this happens. So it's like layers over layers, and at some point they talk, but it's all going over like some custom protocol implementations where a lot of things can go wrong in the parsing. And then we have the more generic smartphone integrations. This is what you may have heard about as for CarPlay and Android Auto. These ones are not for a specific vendor, but everybody who supports it is supposed to work the same kind of way. And the idea is that basically the display of your smartphone is being displayed in a simpler way in your car, and you can use the controls of your car to interact with your phone in a more safe way. CarPlay works by connecting it usually via USB, technically also via Bluetooth, but that's not really being used in practice. And then on top of that is just a TCP/IP connection. Oftentimes it's IPv6, which is being used to talk between the head unit and the phone. And over this, we will have something which is similar to AirPlay, where the display of your screen is being broadcast to the head unit and will be displayed. And then there is a back channel for audio information and for button presses and things like that. Those are being sent back to the phone via this kind of channel.
Thanks. And similarly, Android Auto connects via USB and pairs over Bluetooth. It requires Lollipop on your device, Android 5.0 or higher, and has access to many the car's sensors and inputs. Nothing all that scary on the surface, but you can get a lot of information from these sensors. And we're actually still researching this heavily in our free time to look at how these work. So I think an interesting point about the generic smartphone integration is that this is a move towards having a centralized way to update this kind of software. So instead of relying on an IVI system that has something custom rolled that will probably never be patched, the idea here is that Apple and Google will constantly update these, and you'll just get that on your phone, and you'll have like the new fixes and features immediately. So it's sort of taking the responsibility off the OEMs to update these systems, and it makes things a little bit more streamlined and concise. There's actually fairly little public research about these things. It's hard to find any information. Most of the documents are aimed at developers who want to write apps for this, but not actually like the technical details of how these things work. So we've been having to kind of dig into this the old-fashioned way.
Okay, so that brings us a bit to how can you get started with this kind of research? And when we were looking at this, like, oh, cars are cool, that would be fun to work on, we were like, well, it's probably something like this, right? One car, please, and then you hack a little bit on it, and then you will, oh, I need another car because I kind of found all the flaws in this car. So this is, this is not working for the average person who just wants to hack on these things. Even if you do it for commercial purposes, usually you cannot just buy cars to do research on. So what else can you do? Well, there's a lot of things which are in these systems which we talked about, which you can attack without having a full car. You don't need to have a car to, if you think about this head unit or this IVI system, you don't need to have the entire car connected to check for Bluetooth flaws or to see if you can get into the system via services on Wi-Fi, or if you get a console, how can you get root on it and maybe install malicious things on there, looking at network services, all these things you can do without having an entire car. So what you could do there is actually just get one of those units aftermarket or from a broken car which has been wrecked in an accident or something like this. Also, you can look at the vehicle networks, either on your own car, if you don't actually do anything malicious. If you just want to learn how things work, you can tap into the vehicle network in your own car and just record things and see what's going on. As long as you don't send anything, you cannot really destroy anything or do any damage to it in that sense. Don't quote me on that, though. So what you could do, this is like prices from the US, but you can just go to a junkyard and you can see if you have a car which was in an accident, and you can get one of those IVI systems. And you just need to connect it to power and maybe to get some knobs connected to it to make it run. But then you can have this even like sitting in a rack or just sitting on your table, on your bench, and just play with it. And most of these are working just fine without having any car connected to it otherwise. These are some links which Drew put together for the Argentinian audience here, because we know it's hard for you to get things down here, and you have like limitations on package receiving and customs and things like that. So we heard these sites are a good starting place to get some of the tools we will be talking about in the next couple of slides. So one thing to look at is the canvas, for obvious reasons, and that's also just if you just want to look at your own car and see what's going on. And you can get this adapter, which is called USB to CAN, for fairly cheap, and the nice thing about it is you don't have to worry too much about software. Linux supports it natively. There is a kernel driver for it. You just plug it into via USB, and you get a device, network device, and you can just dump CAN messages right after this. So it's like as easy as it gets. And you can connect it just by putting 2 wires into your car, but the easier way is to just use one of these cables. They just go on one side into this adapter, and on the other side they plug into the OBD2 port in your car, which you have. And then you can just record CAN messages and observe CAN messages that way without having to worry about any kind of wiring issues and things like that. If you want to not look into the CAN bus which is exposed via OBD2, but maybe something which is on your infotainment system, or you actually dig into your car and you find where the powertrain control unit is and you want to listen to CAN traffic there, you can these kind of back probes where you have this long pointy pieces which you can just put in the rear of a power plug which you have in the car. And so you don't disturb what the car is doing, you just tap it basically for sniffing purposes. And then the other side of it, if you're looking at other parts of the car which you might want to look at, we get back to our car hacking, so not car hacking, but hardware hacking and embedded system hacking tools. If you're familiar with JTAG, which is an on-chip debugging protocol where you can potentially dump firmware, you can debug the chip, you can see what's going on there. There's tools like the JTAGulator, or other ones such as the Bus Pirate and the Shikra. Those all speak these kind of protocols, and if you open up one of those head units and you see which pins are exposed, oftentimes the debug pins are still there. So it may be possible that you connect 3 wires and you put a terminal to it, and you could have a root shell on your IVI system. So there's a lot of things to play with fairly simple hardware hacking tools. If you have money left over, or you're working for a company or something like this, you can go the commercial route, but this is going to be really expensive. The cheapest things there, so the state of the art is coming from this company called Vector, and they're having Canalizer and Canoe, and they started like $1,800 for the license, and they can get up to $12,000 for the more professional licenses. So it's like probably more expensive than buying a car which you want to look at, so that's not really something most people will do. But the idea is if you're developing software for CAN and you're writing your own hardware and you want to test it, these things can actually simulate an entire car and an entire car network for you, and you can do it all in software. But again, this is probably, for most people, not really a cost option. And then, so finally, if you are interested in car stuff and you think this is a cool field to get into, there is now a book, the Car Hacker's Handbook by Craig Smith, which came out in No Starch Press. There's a number of papers from researchers, like Charlie Miller and Chris's paper are pretty good as introductions. Checkaway and Kosher and Foster are all academic researchers, which have written papers, and they also give you a pretty good introduction into all the different technologies. And also, if you're heading to other conferences where there are trainings, we had a workshop here at Ekoparty actually about cars, and also other conferences offer trainings. Also, Craig Smith and CAN Bus Hacker offering actually trainings where you can do hands-on car research.
Thanks. So some conclusions we hope you got out of this presentation. Cars present a very unique attack surface and a very complex problem to solve for security people and for OEMs. The sheer number of variations that exist in these network designs presents endless permutations of problems that could happen. Secondly, cars continue to get more and more advanced. People want new features, new things all the time. And this exposes much more interesting attack surfaces over time as they become more connected. And the customer demand for these is so high that they essentially roll them out, and the testing comes after. And that's sort of a broken model that that we're working with companies to help fix. And lastly, car research does not have to be all that costly depending on your intended goal. If you already have knowledge about Bluetooth and Wi-Fi or NFC or Linux system hardening and things like that, there's a lot of things that are directly applicable and you can dive in immediately and start investigating some of these systems right off the bat. So with that, we want to thank everyone. Big thanks to Ekoparty. This is my third talk here and one of my favorite conferences, and I'm honored to be here. So hopefully start on a new talk right after I leave so we can keep coming back. But here's our contact information on Twitter. We'll have slides shortly up after. One of us will tweet it out, so if you want to get some of the access to these materials and look at them later, please feel free. And so with that, we'd like to open up any questions that you might have.
¿Hay alguna pregunta? De todas formas, Daniel y Drew van a estar in the next room for questions.
Yeah, absolutely. If you see one of us, just stop us anywhere. We'd love to chat with anyone about anything, so feel free.
Muchísimas gracias, muchachos.